Good evening, everyone. Thank you for joining us tonight. And it's so great to see so many people here. Last week, Dr. John Cohn gave a fantastic high-level overview of AI. And we want to thank you all for the massive turnout last week and the positive feedback we received from many viewers. Hearing you guys express new interest in AI has furthered our resolve to make AI more accessible to youth through our programs. This is exactly what our mission was meant for. As we all know, AI will have huge economic and societal impacts in the near future. So we want you to get exposed to AI early on so we can utilize this technology for a better future. Beginning this week, you'll be introduced to specific areas of AI in our talks given by experts from academia and industry. Today, Professor Han will talk about efficient machine learning. Next week, we're going to have a Youth AI All Members meeting, so no talk is scheduled. If you're interested in becoming a member, please sign up at our Youth AI website at youthay.org to be a part of our community and explore AI together with your peers. On September 3rd, we'll have Professor Peter Stone to talk about how to best create intelligent agents such as robotic soccer players, autonomous bidding agents, and autonomous vehicles. Dr. Stone is a top expert in machine learning, is the founder and director of the Learning Agents Research Group at UT Austin. Additionally, Professor Stone plays a leading role in the field of robotic soccer as the chair of Texas Robotics, president of the International RoboCup Federation, and having led robot soccer teams to 6 world championships. Before I introduce Professor Han, I'd like to briefly go over the logistics of this talk. Due to today's turnout, we'll be doing Q&A through a platform called Slido. Either go to the URL that I've just put in the chat, or you can go to Slido and enter the event code 93641. Feel free to submit questions throughout the talk, but we'll only be answering questions in a QA session at the end of Professor Han's talk. Now, I'm proud to introduce today's speaker, Professor Han. Professor Han is a pioneer in efficient machine learning and a successful entrepreneur. He was named 35 Innovators Under 35 by MIT Technology Review, and his deep compression techniques and efficient inference engines have made significant contributions to efficient deep learning and are widely followed and used by both academia and industry. He's received many awards, and his research has been highlighted by many newspapers and magazines. On a personal note, I'm very fortunate to work with Professor Han as a research intern at his lab, and I've learned a lot under his guidance, and I'm very grateful to have him here today. Professor Han will talk about how to make machine learning faster and greener. Now, I'll give the floor over to Professor Han.
All right. Hello, everyone. Let me share my screen with my desktop. All right. Okay, there we go. So, Jeffrey, can you see my slides?
Yeah.
Okay, great. Hello, everyone. My name is Song, assistant professor at MIT. I'm very glad to introduce TinyML and efficient AI. So the rise of IoT is the main topic today. So IoT plus AI is the AIoT. So having a lot of amazing applications, such as smart retail. We can get personalized recommendations. We can get a store, a retailing store without any people. And we can have a personalized healthcare, like a small embedded device can measure your body without having to sending everything to the cloud to preserve the privacy and also give high accuracy and mobility. And smart home is a lot of small embedded devices that have AI capability like secure camera, smart blinds, smart thermostat that can adjust the temperature according to each person's habit, and or smart lighting according to a habit. Okay, or smart manufacturing. You can have lots of sensors, barcode, and everything is fully automated without many people. And precision agriculture, where you get many sensor nodes that can precisely decide how much water each plant requires to give a very accurate and also efficient watering and maintenance for the crops. Also for autonomous driving, each car is equipped with many different sensors from LiDAR, radar, cameras, okay, and can have autonomous driving give better safety for the drivers. So if you see all these applications, they require AI on tiny edge devices without having to send the information to the cloud, which have several advantages. So first of all, it can greatly reduces the cost, okay? And don't have to set up a cloud, set up a data center to process all the data. And secondly, it's a lot safer for privacy purpose, okay? So everything is processed locally on edge devices. For example, personalized healthcare, only you have your data without having to send it to the cloud. And also smart home, so the data is only contained within your home, so fully preserving the privacy. And thirdly, it reduces the communication latency, right? You don't have to wait for a long time to sending your videos or the voice or the pictures to the cloud and send it back. So greatly reduces the latency. So the future of AI is tiny. So tiny AI will be the driving force for all these amazing applications. However, there is a big issue or limitation for current AI algorithms. So the amount of computation is growing tremendously in recent years. In this example is the language model, okay? Widely used nowadays in natural language processing. The number of parameters, the model size is increasing tremendously from around 0.1 billion in 2018 all the way to 8.3 billion by NVIDIA in early 2020 and all the way to 170 billion in the summer of 2020 with GPT-3, right? So many parameters in the model means a lot of memory footprint and a lot of requirement for computational resources, making it very difficult to deploy AI on those tiny edge devices. And the second problem is to tune such giant AI model require lots of engineer resources. For example, we have to manually tune the number of channels, the number of layers, to tune the kernels, to tune the resolution, to try out different connectivities, which require a lot of human expertise. Like MobileNet, it required many Google engineers for an entire year for each iteration, from MobileNet version 1 to MobileNet version 2 in 2018 to MobileNet version 3 in 2019, right? So can we have automatic design space exploration to use AI to design better AI to save the human labors? So that's the focus of my presentation today, TinyML and efficient AI. So traditionally, high performance AI serving require many engineers to tune a high performance model. And those models are usually pretty large to have good performance, which require a lot of computation. And on the right-hand side, we want to change this paradigm. We want to enable fewer engineers to achieve as well or even better performance than previously labor-heavy model tuning, okay? And also we want to produce small models that can have less computation, require less memory footprint, that can be deployed efficiently on tiny embedded devices, okay? So AutoML and TinyML will pave the way for efficient AI. So this is a brief summary of the research topics our lab is doing. We target smaller model size, lower energy, lower latency, and fully automated design automation for AI. We work on the full stack between AI applications like efficient video recognition, efficient 3D point cloud recognition, machine translation, and natural language processing. And then we also build automated tools to optimize those AI models to shrink the model size by pruning quantization. And also we have developed two generations of automated neural architecture search methods and received several top awards in those low power computer vision challenges. And finally, we also work on efficient hardware for AI and also AI for EDA. So as a high-level overview, we want to start with AutoML. So traditional AutoML requires a lot of computational resource. For example, a paper published by Google requires 48,000 GPU hours, which will take more than 100K US dollars of cloud compute cost, emitting 11,000 pounds of CO2 emission, right? So this is a lot more expensive than traditionally we just train a mobile net in the conventional method. So traditional AutoML using computational resource to trade for human resource. This is very expensive and it have a huge environmental issue. For example, 11,000 pounds of CO2 equals to roughly 5 trips from San Francisco to New York per passenger, which is really expensive. So the problem is the TinyML comes at the cost of big ML, requiring a lot of computational resource to train and search a good model. So last year, MIT Technology Review published an article training a single AI model can emit as much carbon as 5 cars in their entire lifetimes, okay? So this is really expensive. So deep learning has an outsized environmental impact. We really need green AI to solve the environmental problem of nodes and also reduce the amount of computation required by AI. Okay, so this is a benchmark for common carbon footprint in pounds of CO2 or equivalent. For example, a round trip flight between New York and San Francisco for one passenger is roughly 1,900 pounds of CO2. A human life averaged for 1 year is roughly 11,000 pounds, while American life is roughly 36,000 pounds, maybe more expensive than the average human life. Well, a US car, including the fuel averaged for one lifetime, is 126,000 pounds of CO2. If you think this is already pretty large, the transformer model, which contains 230 million parameters with neural architecture search, requires more than 626,000 pounds of CO2 emission. Okay, so it's really expensive, in almost 5 cars equivalent of CO2 emission. Well, our method published this year cut the cost by 4 orders of magnitude, only 52 pounds of CO2 emission, make it a lot greener. Another challenge is how do we efficiently run inference on diverse hardware platforms? So AI can run on different scenarios. For example, cloud AI, you can run AI models on those high performance GPUs. We also have mobile AI where you can run these AI models on your mobile phones, or even tiny AI, you can run those on microcontrollers, a very small embedded device that's really cheap, like a $10 microcontroller or a very inexpensive Raspberry Pi. Okay, their computation budget differs a lot from 10 to the 12 flops per second to 10 to the 9 flops per second, all the way to millions of flops per second. So how do we design model efficiently across such broad spectrum of hardware devices? Okay, if we do them for each case naively, again, it will require a lot of CO2 emission. Okay, so our solution here is, can we build a once-for-all network? Just build one model, and no matter how many scenarios, how many different hardware platforms you have, we just grab a subnetwork from this mother network without having to retrain them. So this is our solution, the once-for-all network, where we can train one network and then specialize it for efficient deployment across many different devices, be it a data center GPU, or a mobile phone, or even a tiny microcontroller. And all these subnetworks, they can be obtained for free without any retraining. For example, you can grab a larger subnetwork for the cloud servers. You can grab a mid-sized network for the phone, or you can grab the smallest network for microcontroller. And no matter how many scenarios you have, you can reuse the same once for all network. Okay. So again, this is the illustration. We have a once for all network, which is the full mother network. It can born many child networks, like a larger child network for the GPU, a mid-sized child network for the mobile device, mobile phone, or a smaller child network for the tiny microcontroller. And all these child networks don't require any retraining, which greatly reduce the number of carbon emission. Okay, so you just have to smartly train this once for all network, and then you can select different subnetworks for efficient deployment across different scenarios. Okay. Well, the challenge here is how to prevent different subnetworks from interfering with each other. Okay? So you have a larger model, you have a mid model, you have a smallest model. They all share the weight, and we have to prevent them from interfering with each other. And the method we used here is progressive shrinking. So we train the largest network first, and then gradually shrink the network, make it smaller and smaller, which is an effective way to prevent different subnetworks from interfering. And in this method, we can get a much better performance than conventional methods. For example, the blue dots are from MobileNet version 3 from Google. This result is measured on the Samsung Note 10, pretty new mobile phone from Samsung. The x-axis is the latency, how fast does it run? And the y-axis is the accuracy, how accurate can it predict the image? Usually, the higher the latency, the higher the accuracy. But for mobile version 3, here we have 4 different models. You have to train 4 times to get 4 models. But our method, once for all network in red, we train only once, okay? And we can directly grab different subnetworks, and we can get many different subnets completely for free, okay? And have a better accuracy latency trade-off. So with the same latency, we can have a higher accuracy, or with the same accuracy, we can have a smaller latency. And we plotted all the different methods of neural architecture search on this figure. Again, the x-axis is the amount of computation in max. The y-axis is the accuracy. And our method can reduce the computation by up to 14 times less compared with Google's exception. Compared with the exception model, requiring only 595 milli max while achieving 80% top point accuracy. And the size of the model, the circle, indicates the size of the model. The smaller, the better. And this method works really well on diverse hardware platforms, no matter if it is a mobile phone, a Samsung phone, a Google phone, or LG phone, or a GPU from NVIDIA, or a CPU from Intel, or even a specialized FPGA from Xilinx. So given the same accuracy, we can greatly reduce the latency. For example, on NVIDIA GPU with 72% top-line accuracy, we can reduce the latency from 28 milliseconds to only 12 milliseconds. A lot faster. And also we can, this method received several awards in the Low Power Computer Vision Challenge to design a small network that have to have a latency less than 7 milliseconds on the Qualcomm Snapdragon SoC. Finally, we can achieve only 5.15 milliseconds while achieving 78.8 top-point accuracy on this Qualcomm DSP. Also, this method works really well on specialized architectures, have a higher arithmetic intensity, and also achieved GOPS per second, higher throughput. And if you see for different hardware platforms, this automated design tool chain can design specialized neural network architectures for Xilinx FPGAs, for Intel CPUs, and also for NVIDIA GPUs. Different hardware prefer different model architectures. Therefore, you see the architecture is quite different. And this is very hard to hand tune by human. And to show you some visualization, this is before acceleration, a super resolution demo. So on the left-hand side is the low resolution video. On the right-hand side, the AI model can build a higher resolution model. Okay, you see they are moving very slowly because the frame rate is really low, only 16 frames per second. This is due to this application is really computationally intensive. Okay, you have to make pixel-wise prediction to predict every pixel from the input to the output. As a result, you see the animation is moving really slowly, only 16 frames per second. You see under the tree, there seems to be a hole where some animal is hiding within the hole. Due to such lagging, it's very challenging to perform real-time super resolution. For example, if this is your TV, you don't want to watch some cartoon at such low frame rate. See, it's giving a really poor experience having such low frame rate. Okay, and in the contrary, as a comparison, our model after acceleration, we can run much faster for the same piece of video. You see the bird is moving much faster, 41 frames per second. Everything, the world is just getting fast. The animal just hiding underneath the tree will get out really quickly. And you can enable this real-time image processing for your TV to turn a low resolution video into a high resolution video, okay? All right. And here we have another demo for running these person detection on edge devices. And the actor here is Jeffrey. Let's watch the video.
Today, I'll be demonstrating our submission to the Visual Wake Words Challenge. This challenge was whether we can detect if there's a person or not a person in a given image. However, this runs on an IoT device and has to fit in a very tight computational budget. The model had to be under 250 kilobytes, run at less than 250 kilobytes of peak memory usage, and have less than 60 million multiply ads. In today's video, I'll be demonstrating our model on two platforms, the Raspberry Pi and the Google Pixel 3. So without further ado, let's start with the demos. For our first demo, let's take a look at the Visual Wake Words model deployed to the Raspberry Pi 4, which is a very affordable device coming in at only $35. Our model is able to achieve 94.58% accuracy after quantization. So let's see the model in action. So currently the webcam's not pointing at anything, so there's no person detected. But if I move into the frame, immediately we can start to see that there's a person that's being detected by the camera. Now that I walk out of the frame, you can start to see that no person is being detected. Now let's try a more challenging case. So if I have my friend just peek his head over the top of the table, you can see that the model is still able to detect him, even with only his face shown. And now if he fully stands up, the model is able to detect him instead. And if he moves out of the frame again, the model classifies that there's no person in the frame. Now, let's see how our model performs on the Google Pixel 3. So as you can see, it can do a very good job of detecting people very quickly and with very high confidence. This model also has very low latency.
Oops. Oops, sorry for the interruption.
How our model performs on the Google Pixel 3. So as you can see, it can do a very good job of detecting people very quickly and with very high confidence. This model also has very low latency because as you can see, we're doing a live image stream with quick, sharp camera movements, and the model is still quickly reacting to those changes. This model also performs well in more complex scenes, such as this lab environment. Even though there's multiple people and plenty of objects and occlusion, the model still can predict whether there's a person or no person in the image with very high confidence. In order to create a model that would perform both accurately and efficiently, we used proxyless NAS and hardware-aware quantization. We used proxyless NAS in order to search a model architecture that would perform well with respect to the hardware that we were deploying the model on, and we use hardware-aware quantization to quantize our model in such a way as to best utilize the hardware architecture. As mixed precision methods such as hardware-aware quantization aren't supported on most standard architectures, we only use hardware-aware quantization for one of the tracks of the Visual Wakeboards Challenge. We are humbled to have been able to place first in last year's Visual Wakeboards Challenge and would like to thank Google for their support and for hosting the competition.
Okay, so this is the demo that Jeffrey did with our lab by spending only one summer at MIT doing this amazing, amazing project. So this illustrates the interesting part where we can deploy those neural nets on those edge devices like a mobile phone or Raspberry Pi. Okay, and beyond that, we recently deployed these neural nets on even more challenging scenario like a microcontroller.
Hi, in this video, we will be demonstrating MCU now. So first, let's take a look at our platform. The board is equipped with an STM32F746 MCU, a very low-powered and affordable device, which costs less than $10. It features 320 KB RAM, 1 MB flash, and an ARM Cortex-M7 core, which runs at 260 MHz. In this demo, the LCD on the board shows a capture frame where there is a person frame. If a person is being detected, the LCD will turn into red, otherwise the LCD will turn into green. Let's see a few clips to compare MCUNet and MobileNet V1 running on TensorFlow Lite micro. If we use MobileNet V1 and TensorFlow Lite micro, the accuracy is about 75%, and the FPS is 2.9. On the other hand, MCUNet can achieve 87% accuracy at 7.3 FPS, which is faster and more accurate by a systematic framework that jointly designs the efficient neural architecture and the lightweight inference engine by TinyNAS and TinyEngine. TinyNAS automatically handles diverse constraints like latency and memory under low search cost, and it is co-designed with TinyEngine, a memory-efficient inference library which adapts the memory schedule according to the overall network topology to expand the design space and fit a larger model.
Yeah, so this demo shows we are able to run the person recognition on only $10, very small, very tiny embedded device that you see. The memory is only several hundred kilobytes, right? Only several hundred kilobytes, making it very feasible for deployment on edge devices. Okay. All right, so far we talk about efficient image recognition, and beyond that, we want to recognize not only still images, but also those moving videos, okay? So video is getting very popular. Like on YouTube, more than 300 hours of videos are uploaded per minute. It's growing exponentially. And we want to understand people's activity in the video stream. For example, whether a person is passing out or something emergent happens. Okay, and you can imagine understanding video requires more computation than images because there are multiple frames sequentially, and we need to model those temporal, do those temporal modeling. Okay, for example, given these 4 different frames, people cannot tell whether you are putting something from left to right or right to left by seeing only one image. For example, if you just see this one image, you cannot tell whether you're moving left to right or right to left. So you have to watch this entire video stream. That is the temporal modeling. And for temporal modeling, people previously used 3D CNN, which can perform joint spatial temporal feature learning, but it's very computationally expensive. 2D CNN is more efficient, but it cannot handle those temporal modeling. So we aim to achieve the 3D CNN performance at 2D's complexity. Okay, and as a result, we just propose this temporal shift module, which we can shift those channels, which require 0 flops and also 0 computation. And these are the data sets that we are working on. Can recognize people's gestures, like you are swiping something, you are thumbing up on the gesture data set. Okay, and also we evaluated on the less temporal related data set, like people applying eye makeups, applying lipstick, etc. And as a result, we can greatly reduce the amount of computation from roughly 600 gigaflops per video all the way to only less than 100 gigaflops per video, while the accuracy also increased from those green and blue dots all the way to these orange dots. And here is some demo showing the speed up of our model compared with the 3D CNN running on the NVIDIA GPU. Conventional i3D method has a latency of 160 milliseconds per video. You see it's moving quite slowly. And the temporal shift module, you see, is running much faster. Okay, only 70.4 milliseconds per video, 9 times speed up. If this is a self-driving car, it means you can recognize those dangerous activities much faster at a much lower latency compared with conventional model. Okay. Here is another demo showing the speed up of the throughput. Conventional i3D method, the 3D convolution it achieves 6.1 videos per second with the accuracy of only 41.6. Okay. Without changing the hardware, we can run with even better accuracy, the model at 77 videos per second, which is 12.7 larger throughput. Okay, so given the same computational resource, now you can recognize 12 times larger amount of videos. Imagine you are analyzing those YouTube videos. Now, overnight, you can recognize more than 12 times more videos compared with the conventional method, which greatly improves the efficiency and the productivity. Not only the speed up, but also the accuracy. So here we are detecting a car. On the left-hand side is the conventional method, RFCN, which watch individual frames individually. And sometimes 2D baseline give false positive prediction due to the flare. Misclassify the car as a train, okay? Because the train sometimes have a high beam light. While the temporal shift module gives very robust recognition throughout this video, even there is a flare of the beam light. Let's watch it again. The left-hand side, false prediction. The right-hand side, a very smooth and correct prediction, because the right-hand side, we have we are not watching frame by frame, but we understand JSON frames and the sequential relationship. It was a car in the previous frame. It cannot suddenly turn into a train to the next frame. So by this temporal modeling, we can make the prediction much more robust. If you are a self-driving car provider, this will make the service a lot safer to prevent those misclassifications leading to accidents. Okay. These are some quantitative results, higher accuracy. And we are able to deploy these video recognition modules on very low power embedded device like even a Raspberry Pi, taking only the power, roughly a LED bulb, really efficient, but can run at almost real time. For example, on Note 8, we can run at 29 frames per second. On Raspberry Pi, it's 14 frames per second. Okay. So this model is not only efficient for inference, but also efficient for training. For example, thanks to the collaboration with IBM, we are able to scale up the training of video recognition models on this large-scale distributed training infrastructure. So here we reduce the total training time from 49 hours and 15 minutes, almost 2 days, to only 14 minutes. Imagine a work you have to finish in 2 days. Now you can finish just over a cup of coffee, 14 minutes. So it's really amazing when you have a lot of computational resource and also efficient model that can scale really well. The theoretical speed up is 256 times. The actual speed up is 211 times. And also we can understand what is happening in this video understanding model. For example, we can do spatial temporal localization. Like in the first video, moving something away, the highlighted parts in the temporal part is highlighting frame number 3, 4, and 5. And the regions are exactly showing we are moving the cup away. And in the second video, in frame 1, 2, and 3, we are moving the cover away. And in the third video, it automatically annotates the 4th, 5th, and 6th video frame where we are moving the basket away, and only the basket is highlighted. So this model is very interpretable. And this is another example showing the action of wiping. So you see the hand and also the paper towel is highlighted in the first image, in the first video, and also the second and third video. Okay, and also push something to the left. It magically highlighted the regions, the cup and the hand, showing we are pushing something to the left, including the second and the third video. Including flipping, another example, flipping book pages. We are exactly highlighting the frames and the region where we have a hand, and also the book where we are flipping the page. There are even more interesting examples. You are very welcome to check out these examples on the paper. For example, in the middle, conventional method, TSN is not interpretable. It's not highlighting the correct region where we are plugging something into something. But our model is not only efficient, but also can tell where and when you are doing this action. Finally, this is a demo. We are running a $99 NVIDIA Jetson Nano with really high frame rate, doing this real-time gesture recognition. And we can further build a model.
My name is Josh Noel, a current master's student in MIT.
Further build a model to control the Google Map with the gestures. It's running again locally on this NVIDIA Jetson Nano at real time. Everything running on this embedded device. For example, we can zoom in the map just with your gestures. On the right-hand side is what the Jetson Nano is seeing, or you can drum the finger to enter the street mode to highlight those roads. And then you can swipe to change your position in the map. And you can hold to stop the map. You can thumb up to enter the street view. This is very helpful when you are trying to remotely control something, especially under COVID. You don't want to touch, okay? Touchless. And you can hold to stop the swiping. You can zoom out completely with your gesture, no touching, no contamination, no, just purely using your gestures at real time. You can drum the fingers again. You can exit the street view mode to get back to the normal mode. You can drum the fingers again to go to the normal map mode. Okay, so this is just showing the powerful algorithm that can understand the activities in real time. And I think given COVID, for example, you want to control the elevator when you're going back home, but you don't want to touch the elevator. You don't want to contaminate your hand. You can imagine we have this device in the elevator. It will be very helpful for you to remotely control the elevator without having to touch it, make it a lot safer under COVID. Okay, and this is another interesting demo on the something data set. Given the video on the bottom is the prediction, like hitting something with something or moving something away from something, covering something with something. So the AI model is recognizing this video very accurately, moving something away, rolling something on a flat surface, put something on a surface, taking something down, etc., hitting something with something. Okay, moving something up. Okay. All right. So having talked about video recognition, my next topic is about 3D deep learning. Okay. So far, we talk about everything is in 2D, no matter it's 2D video or 2D image. But the real world is 3D, okay, three-dimensional. Like scene segmentation is very important for AR and VR headsets. Object detection in the three-dimensional space is very important for self-driving cars, and also particle discovery for high-energy physics. The sensor for 2D is a camera, and the sensor for 3D point cloud is the 3D LiDAR sensor, which is very widely used nowadays in autonomous driving cars. Okay, 3D point cloud, there are usually more than many points in the X, Y, Z intensity format of representation. But traditional conventional 3D deep learning require a lot of computational resources. As a result, on the right-hand side, these people playing a VR AR game has a full backpack of computers. Okay, very heavy, very bulky. On the right-hand side is showing a self-driving car with the whole trunk of computers, because these sensors produce a lot of data at high frame rate and have to need to require a lot of computation. And this is another scenario where TinyML can help reduce the computation. This is showing a difference between 2D model and 3D model, an order of magnitude increase of the inference cost, and more than 4.5 times increase of the training time, which leads to low resolution. So if you cannot afford so much computation, one person becomes only like 5 points after very aggressive downsampling to save the computation, which is a really bad idea. So aggressively downsampling indeed can reduce the computation, but also leads to safety issue, right? For the right-hand side, the red is the fading case. The green is the recognized case. Sometimes you cannot recognize a person. It's shown in red. This can be very dangerous for autonomous driving. And as a result, you see this is a real Model 3 Tesla car in autonomous driving mode. Missing this person suddenly appeared behind this van, running at only 30 kilometers per hour. So it can get really dangerous if we don't recognize those small objects very properly. And by the way, Tesla is not equipped with a LiDAR sensor due to the high cost, but it will lead to severe safety issue. So we propose this method called sparse point voxel convolution, which can greatly reduce the amount of computation by combining both the coarse-grained voxel-based feature aggregation and also the fine-grained point-based feature transformation. It's a very efficient method that can recognize those small objects like the person, the cyclist, the trunk, the traffic sign, which is highlighted here, that was recognized by, on the bottom, the point-based feature transformation. And these small objects are usually very important, like the person, the cyclist. You don't want to hit the person, you don't want to hit the cyclist. They are small, but they are important. So this is showing the speed up comparison. On the left-hand side is the point net. On the right-hand side is our PVCN that can run 1.8 times faster doing this 3D indoor segmentation. Like here, the table is colored in red, the walls are colored in green, for example. Our method already finished, and it's much faster and more closer to the ground truth. This is another demo for 3D outdoor detection. So conventional method runs 10 frames per second. Our method can run 17 frames per second. On the top is the 2D image detection and the object detection. The bottom is the 3D object detection. Our method already finished this video stream, while the baseline method is still making progress. This is another demo of a self-driving car navigating an intersection. Previously, the method can run 3.4 frames per second, requiring more than 100 gigaflops per frame. But now it requires only 30 gigaflops per frame, and almost 2 times faster. So different objects are colored with different colors. And compared with projecting everything into 2D, which have a lot of loss of information, it will require a lot of extra parameters, which is highly inefficient. Like darknet require more than 370 gigaflops per frame, while our method reduces it by 30 times, right? Only 10.6 gigaflops. Well, the accuracy is much higher, and the error map on the right-hand side is you see much less red, which means less error. Real application is deployed. Our method is deployed on MIT driverless, which is a fully autonomous racing car participating in the competition every year. You see there's a LiDAR sensor in front of the car. That's exactly where our algorithm is deployed to process the sensor, the data collected by that sensor, to recognize those cones so that we can better navigate. This is our team. We want to have a low latency and also high accuracy. So this is the demo showing the baseline method versus our method detecting the cones. The left-hand side is the yellow cone is on the left. The blue cone is on the right. We want to distinguish left and right so that we know where is the track. The conventional method runs at only 95% top-line accuracy, seeing a range of 8 meters, while our method is having accuracy of 99.93% top-line accuracy, can detect a range of 12 meters, okay, a lot farther, okay? And the latency reduced from 2 milliseconds per object to only 1.25 milliseconds per object. This is another demo showing the real deployment of our method on the autonomous car. You see it's fully autonomous without any human intervention. It's passing through this turn very smoothly. There are 2 cameras, so we can concatenate them together. On the top is what the LiDAR sensor is seeing, and the bottom is what the camera is seeing. So it can detect the left and right cone very accurately. So in summary, I think the more and more applications are enabled by 3D deep learning, such as the iPad Pro 2020 starts to have the LiDAR scanner, and also LiDAR is also widely used in many autonomous driving cars. So our method for efficient deep learning, shrinking the deep learning's carbon footprint, is also covered by MIT News recently. So such method will have a very broad application in the future. So Jeffrey, do I have the extra minute, or we have to conclude at this moment? It's already an hour.
Yeah, if there's anything you
Jeffrey?
want to go over, yeah, I'm here. So if there's anything you want to go over, I think we have a bit of time, but I also want to get to Q&A.
Okay, yeah, so I think it's a good point where we covered the computational efficiency side. And finally, I just want to show one very quick result showing the data efficiency. For example, data is very expensive. to achieve all these amazing results, people have to collect a lot of data. Like ImageNet has 1,000 classes, more than 1 million images, which is very expensive to collect. So can we have a very awesome model, but only with fewer images? So here we present the few shot comparison. Just use 1,000 images to generate a person using generative adversarial neural networks. So conventional methods like StyleGAN2 cannot generate people at high quality. Like this is me, it's fully distorted. But with our efficient method called the GAN augmentation can efficiently generate images with just very few images. Like this is very photorealistic, looks like me a lot. So in summary, here we talk about the efficiency of AI, where we want to deploy AI on those on-device scenarios that require less computation, less memory, and also less data. Okay, we aim for energy efficiency in AI model training and also AI model inference. We want to reduce the carbon footprint of artificial intelligence for a more environmentally friendly approach. We believe such algorithms and hardware co-design will lead to many AIoT applications in the future. And if you're interested, here is a complete reference papers that you are welcome to check it out. And you are welcome to subscribe to our YouTube channels. And also our code is available on GitHub. Welcome to check out our papers, presentations, and code. Okay, that's all for my presentation. Thank you.
All right, so everyone, just as a reminder, if you have any questions, please submit through Slido. So I'm just going to start from the top of the list right now. There's several questions that are all related to roughly along the gist of how should beginners get started in respect to several things. So firstly, it's just for beginners who don't have any programming experience but are interested in getting into AI, like what would be your advice in getting started?
Okay, so I recommend first make you feel passionate about this amazing discipline. Okay, when you are passionate about something, then you can learn something really well. And then probably you should learn some basic programming for sure, like Python programming, and also some basic math, like basic linear algebra and probability. But I recommend start something by doing. So you start to learn by a project rather than learn purely from textbooks. Combining the practice with the learning is the best learning approach.
And kind of in a similar vein to that, for people who maybe have more experience, what opportunities like would you recommend for people who are trying to, for instance, like start their own AI projects or get involved in research?
Yeah, I think Jeffrey is a very good example. I think when Jeffrey started, I can tell the story where um, I first give Jeffrey a starter project by the Google, what is the kit called? The Google Voice
AIY, yeah.
AI, AIY kit. Yes, AIY kit. So it's available on Amazon where you can um, do speech recognition, keyword spotting, and also some simple image recognition by this AIY kit. So it requires only a few lines of Python programming, but it's pretty fun and really hands-on project. You can have a real box. Maybe Jeffrey, you can share some of your experience playing with starting with a simple project and how it lead to your next project. Maybe you can
Yeah,
share.
sure. I can talk briefly about that. I think once you've kind of gotten that beginning experience in programming, like once you feel comfortable with programming, you have some fundamental idea about like AI. There's plenty of great online courses that you can learn that. I think for sure, certainly just start with a project and try it. I've learned the most just by trying things and just seeing if they work or not. Sometimes things don't turn out well, but just through the process of, I think that's how a lot of projects you should really approach, just as something where you're more in it for like a learning experience rather than something you're trying to concretely get like a research result out of or something. Just like AI is one of those fields which I really feel you gain the most experience simply just by trying things.
Yeah, exactly. I think that's a super fruitful summer where Jeffrey started with that simple demo all the way to this complicated visual wake word demo. I think it's a um, pretty good experience that you can share with your classmates.
So moving on, kind of, so another question that someone had was, how do you think that current autonomous driving programs will progress in the future alongside AI development?
Yeah, I think some the autonomous driving level 2 is available in many cars, but I think there's a long way to go before it can get really safe. Um, the most important thing is for dealing with those corner cases, right? For example, for those normal case, it's usually pretty easy to conquer. Like you can recognize these cones, these simple objects, those trees, people, pedestrians, and bicycles very easily, right? But when you have these corner cases, like in this case, where the person is appearing right behind this van, this is very challenging. Like this person is super small, and also is hidden behind this van previously. So I think multiple sensors is very important and very critical, not only cameras. But another challenge is the cost. So LiDARs can be super expensive these days. The LiDAR can you can afford is not it can range all the way up to like 50K US dollars, which is almost the cost of a normal car. So there's still lots of challenges, computational requirement, the cost of the equipment, um, but I think with the growing um, technologies for model compression and efficient AI, I think we can gradually reduce the cost of processing those sensor data. So um, that requires the efforts of all of us.
All right, so I think moving on to the next question. So someone's asking whether these problem limitations with, especially with limited computational resources and also just expensive training costs and also the environmental impact, whether the rise of quantum computers could, what kind of effect would these new types of computers have on these issues?
I'm not expert in quantum computers, but I think that's a very active research area. Um, might lead to some fundamental changes, but I'm not expert in that domain, so maybe I recommend you check out some more related um, Wikipedia topics.
Yeah, and then someone's also asking whether once for all could kind of be compared analogously to stem cells and stem cell growth treatments, and how stem cells start off more generally and then they later specialize.
Oh, the stem cell. Okay. I think we did try the once for all network where you have different tasks. Like you can have a stem cell and then we get into very different cells. I think it's a very interesting analogy. Um, but the difference is these child networks no longer require any training, but the stem cell throughout the lifetime it continue to evolve. So I think that's the difference. So this child network, from the computation perspective, we want to have this mother network born many child networks, and many child networks doesn't require any training. You can just directly grab it and use it for different deployment scenarios.
Well, all right. One last question, and I think it's almost an hour. So uh, someone's asking about the cost of labels, and they're asking what's your opinion on semi-supervised learning and the rise of in non-supervised methods.
Yeah, I think that's a very good question. The labeling can be quite costly. Those labeling require months or even years of considerable human efforts, right? And along with the prohibitive annotation costs. So self-supervised learning is getting very popular these days. For example, you can extract the features from the same image, but with different distortions, but they belong to the same image. Um, for using or using different or using the contrastive loss, people have built methods that can almost rival the supervised learning's accuracy. So that's a very hot topic, moving really fast. So I think that's a very meaningful direction. Also, President Ray from MIT also mentioned the data efficiency is super important. New direct um, this is not about solving incremental problems. Like in artificial intelligence, the focus would not be further refining current algorithms, but rather developing profoundly new approaches that enable machines to learn using much smaller data sets and a fundamental advance that would eliminate the need to access immense a lot of data sets. Okay, and we are showing so far a pretty good example using only a few images, but can obtain really good results. So all these results are generated using only 100 images from Obama, Grumpy Cat, Panda, Bridge of Sight, etc. So fewer images, but equally good quality. Okay.
All right, so it's past 8:30. Yeah, thank you, Professor Han, for your time. Uh, it was great having you to talk about efficient AI, especially its implications in a world where climate change and its impacts are increasingly becoming more important. So yeah, it was great having you here, and thank you again for giving your time.
My absolute pleasure. Thank you, Jeffrey.
All right. And just as a brief reminder to everyone, in 2 weeks from now, September 3rd, we'll be hosting Professor Peter Stone from UT Austin, who is going to talk about uh, autonomous agents, especially his experience in robotic soccer. So if you're interested in that talk, we should send out an Eventbrite link soon as well. Or if you're interested in becoming a member of our Youth AI site, we can have, you can register there. We provide peer-to-peer mentoring, and we're hoping to build this community where people interested in AI can collaborate, meet, and work together. All right. Thank you everyone for attending, and I wish you all a great night.